Okay, welcome guys to Physics 390 Class 5. In this class, we'll be talking about the TISE or time-independent Schrodinger equation applied to the harmonic oscillator. And this is chapter 2.32 of our textbook. Okay, so we're going to be solving the quantum harmonic oscillator with what's called a power series method, which is an interesting method that's used for challenging differential equations. Okay, so there's more than one way to skin Schrodinger's cat. Okay, the time-independent Schrodinger equation shown here, which we looked at in the last video for the quantum harmonic oscillator, can be solved using a power series method as well as by the ladder operator method, which we looked at last time. Okay, so let's see how this might work. First, we just clean up some variables and put this equation into a little bit more compact form. We define this Greek letter psi as the square root of m omega over h bar times x. And we defined this k as the scaled energy. It's really E divided by h bar omega over 2, where h bar omega over 2 is the ground state energy of the harmonic oscillator. So k is linearly proportional to the energy. It's just another way to write it. So if we substitute these in psi for x and k for e and do some rearranging, we can write this TISE in a more compact form. And it looks like this. The second derivative of psi with respect to c squared is c squared minus k times psi. Okay. So, all right. So, how might this behave, and how might we get to a power series solution? So at large x, if x is large, then this variable c, this Greek letter c, must be large since they're proportional. So at large c, this c squared is going to be very large compared to k, because k is just a finite energy, where c is a position or a scaled position, which can get extremely large. So at large c, this minus k drops out. We get the second derivative of psi with respect to c squared is approximately equal to just the c squared psi. Okay. And it turns out that's approximately solved by psi approximately equal to a e to the minus c squared over 2. Okay. And you can verify that by taking the second derivative of this and comparing it to just taking the c squared and multiplying by this expression here, and you'll see that they are approximately the same. Okay, so where does that get us? Well, it shows us that there's some kind of behavior going on at large distances or large c, this e to the minus c squared over 2. So given this, what we call asymptotic behavior, that is for very large c, is a e to the minus c squared over 2, we can try an inspired guess to simplify things. And so we write the wave function psi of c as h of c e to the minus c squared over 2. Okay, so we're building in this asymptotic dependence, which we've seen. We've given an argument that it exists at large values of c. So if we take this new expression, h times e to the minus c squared over 2, and insert it back into the time-independent Schrodinger equation, that is this equation here, insert that in there, and simplify things, we get a new equation involving only this h. Okay, this h, this part that we've separated out from the e to the minus c squared over 2. And this is the equation here, the second derivative of h minus 2 times c, the first derivative of h, plus k minus 1 times h is equal to 0. Okay, so how can we approach this? It's a little bit, it doesn't look like trivial. And in fact, it has two terms in it, two derivatives, and it even has the variable here. But what we can do is apply a very versatile method for differential equations called the power series method. And we represent h as a power series. So we write h as a function of c as a constant plus some second constant times c plus some third constant times c squared, and so on up to c cubed and fourth and so on. So this is like a Taylor series, but this is a power series for c. And it can be written as a sum of j equals 0 to infinity of aj c to the j. That just represents this series here. Okay. So then to see if this can help us, we've got to differentiate this series because we have dh dc and the second derivative of h dc squared here. So when we take the derivative of h with respect to c, we get, I won't do all the terms, but the first term is the derivative is 0 since it's a constant. The second term, since it's linear in c, just gives a1, which is what we see here. The third term gives 2a2c, which is what we see here, and so on and so forth. Okay, and we can write that in an abbreviated form as the sum from j equals 0 to infinity of j a to the j c to the j minus 1. So example for j equals 0, this gives 0, since 0 is j 0 zeros this out. For j equal 1, this would be 1 times a to the 1 times c to the 1 minus 1, or c to the 0. So it would just give a1 as this is here. So this is the series representation of this series here that comes from differentiating the power series. And then we can do the same thing with this series, differentiated again. I'll just do the first term. So a1 disappears since it's constant. 2a2 c gives 2a2, and so on. This would give 2 times 3a3c, which is what we see here. And then we can also write this as represent this as in terms of the arbitrary j as sum of j equals 0 to infinity of j plus 1, j plus 2, a to the j plus 2, c to the j. Okay, so just for example, for j equals 0, we'd have 0 plus 1, 0 plus 2, so that's 2 times 0 plus 2, so 2a2, and then c to the 0 is 1. So 2a2 should be the first term, which it is. Okay, and the rest of these terms, you can verify that they match up with what you'd get if you plug in 1 for j, 2 for j, and so forth. Okay, so we're trying out this power series, and we have expressions for the power series, for the derivative of the power series, and the second derivative of the power series. Now we're going to plug those back into the differential equation. So this series here will go back in for the second derivative. This series here will go in for the first derivative here, multiplied by c. And then this original series, power series here, will go in for h. And inserting those in to the differential equation and gathering terms, adding up all the terms that we get, gives the following. Sum j equals 0, j plus 1, j plus 2, aj plus 2, minus 2j aj plus k minus 1 times aj, cj equals 0. Okay, and here's where we use the real important property of power series, which is that if this power series is going to be 0, it's a power series in C. So if any of these terms in brackets was not zero, then that would make the sum not zero, because if C was, say, 1, all these would be added together. So each, for every J, this series must be 0. Okay, so when we have a power series and it's equal to 0, the coefficient of every term of the what's raised to the power here, the C here, has to go to 0. So that's saying the coefficient of Cj must vanish for every J. So that means that this, what appears in brackets here, J plus 1, J plus 2, etc., must be 0. Okay, so that's kind of interesting. And we can use that to set up something called a recursion relation, which relates the coefficient aj plus 2 to aj, because you see the only things that appear in here are aj plus 2 and aj, and they have to equal 0. So if we solve this for aj plus 2, we can, if we knew aj, we could immediately get aj plus 2. So that's what we do here. So solving that last expression gives a recursion relation for aj plus 2, which is 2j plus 1 minus k over j plus 1, j plus 2 times aj. All right. So if we were given an initial a0, that would generate all even an. So from a0, we would plug in, and also a value of k, we'd plug in j equals 0, and we would get a2. And then we take the a2, j equal 2, plug that in here, and that would give a to the 2 plus 2 are 4. And we take 4, plug it in here, and this would give a to the 4 plus 2 are 6. Likewise, if we had a1, it would generate all odd an. So if we started with a1 and k, we could solve for a3 by plugging in j equal 1. And then once we had a3, we plug in j equal 3 and get a5, and so on and so forth. So this recursion relation, given either a0 or a1, gives us all of the coefficients, the even coefficients for a0 and the odd coefficients for an. Okay, so here's where the important argument comes in that allows us to solve this and get quantization, that is, particular values of the energy. So at very large J, the recursion relation becomes approximately a to the j plus 2 is 2 over j aj. Okay, so to see that, if j is very large, we can ignore the plus 1 minus k. So the numerator will just be 2j. The denominator will be, if j is very large, we can ignore the plus 1 and the plus 2. So the denominator would just be j squared. So we'd have 2j over j squared, or 2 over j. So aj plus 2 would be 2 over j aj. And it turns out that has an approximate solution. aj is approximately equal to some constant over j over 2 factorial, okay, which you can get if you plug in, if you put in j plus 2 here, this becomes j plus 2 over 2 factorial, or j over 2 plus 1 factorial. And if you take that, the ratio here of aj plus 2 to aj, you get, actually you get 2 over j plus 1. But since j is so large, that's essentially the same as 2 over j, which is why it's an approximate solution. So anyway, we get this approximate solution. And with that approximate solution for aj, that gives us a formula for our polynomial h, which we've been after, that's going to give us the wave function. So h is going to be aj, the sum over j of aj psi to the j. But for large j, that's c over j over 2 factorial. And since this is a dummy variable, this j, we might as well, instead of using j over 2 factorial and e to the j, we can just use not e to the 2j, but psi to the 2j, psi to the j. We can switch that and double both of these. And we just, since it's an infinite sum, we just get 1 over j factorial psi to the 2j. And this actually is an expression for a Taylor series with the c out in front. So the Taylor series for e to the x is 1 over j prime x to the j. So here our x would be this psi squared, because psi to the 2j is the same as psi squared to the jth power. So we get 1 over j factorial psi squared to the jth power, which is approximately equal to e to this quantity, which is psi squared. Okay, so that's a lot of approximations and arguments and stuff. So now, why is this important? Well, for the wave function, this gives psi. Remember, psi was equal to h times this factor which we pulled out, this asymptotic factor, e to the minus psi squared over 2. So that would be, so given this expression for h that we found for large j and very large j, that would be c e to the psi squared, e to the minus psi squared over 2. But e to the psi squared, e to the minus psi squared over 2 is e to the psi squared over 2. So that means that this is e to the something positive, and psi depends on x. So as x gets much bigger and bigger, psi would get much bigger and bigger, and so the wave function would get much bigger and bigger. So it's going to diverge, the wave function will diverge at large values of psi, or large x. And so it wouldn't be possible to normalize the wave function, because this wave function is this e to the psi squared over 2 is just going to blow up as x goes to infinity and psi goes to infinity. Okay? So something must give here. And the only thing we used here was that we had very large j. So it must be that we don't get to very large j somehow, or don't get to extremely large j. And so what happens is it follows that for the wave function to be normalizable, the series aj must terminate before getting to large j. In other words, we don't start with a0 and build up a2, a4, a6, all the way up to a infinity. There's some finite number of terms that we get to. So we don't get to very large j and have this blow up of normalization, or blow up and lack of normalization. Okay, so oh, and I just I put this in here to just as a reminder that this technique of a power series being required to terminate because of normalization considerations like we have here actually is not, it works for the harmonic oscillator, but it also works for the hydrogen atom, which we'll be looking at later. So this idea of the power series needing to terminate so that the power series doesn't blow up is going to come back again, and we'll see it again in the hydrogen atom. Okay. So the numerator in the recursion relation, this recursion relation up here, must vanish at some value of j, so that so the next value of a to the j plus 2 is 0, and the power series terminates. So giving, and just to make it look familiar, instead of j here, we'll use n. But if this is going to vanish, we're going to have k is equal to 2j plus 1, but we'll use n here just because that's what we're familiar with. So it'll be k equal 2n plus 1. That will make this numerator 0 if k is equal to 2j plus 1 or 2n plus 1. But k was defined as, so k equal 2n plus 1 But if we look back, K was defined as 2E over H bar omega. So that was just a way to make the equation appear more convenient. So we have 2E over H bar omega. And solving that for E, we get, dividing by 2 first, we get n plus 1/2. Multiplying through by H bar omega, we get H bar omega times n plus 1/2. Okay, and hopefully that seems familiar because that's exactly what we got for the nth energy, where n was an integer, 0, 1, 2, 3, 4, etc. For the ladder operator solution. Okay, so we get the same expression for the energies as we get for the ladder operators using this idea of power series. But the idea is that we're only allowed certain values of E because those give us certain values of K, which when put in this recursion relation, cause the series to terminate. For the wrong value of E, the K that we put in here will give an infinite series of AJs, and then we'll get a non-normalizable wave function. Okay, so that's the restriction. Okay, so so we have the energies. If we want to find the polynomials associated with each energy, we use this recursion relation with K determined by our En. Because remember, as we just saw in the last slide, K is, if we know E, we can find K. So for example, for the ground state, E is H bar omega over 2. So this would be 2 times H bar omega over 2 over H bar omega, which would be 1. So K would start out as 1, and we would have 1 here for K. And then we would just build up this series, and at a certain value of J, in fact, it would be J equal 1, this series would terminate. Okay, so so that allows us to take the energies which we have, the n plus H bar omega times n plus 1/2, find these values of K, and use this formula to figure out the coefficients and find the polynomials. Okay, so once we get the polynomials, we can get back to our wave function, because our wave function is this polynomial times e to the minus psi squared over 2. So re-expressing this in terms of x and normalizing, because we always want normalized wave functions, we get this. Okay, so we get associated with our En, we have psi n of x is this coefficient out in front times 1 over the square root of n factorial. We also have a 1 over 2 to the n times this capital Hn, which is written in terms as a function of still psi, but psi depends on x, so we could plug this in and it would be a function of x. This function here is the same as little h of n. It's just normalized, or it's multiplied by a constant to make this normalization have a neat formula. Okay, so this matches the form we got when using the ladder operators. Okay, so we had this same m omega over pi h bar to the 1/4 out in front. We had the 1 over n factorial. We had a polynomial in x, and we had e to the minus something with x squared over 2, which is what we get when we expand this psi out in terms of x. Okay, and just for your information, these Hn of psi are called the Hermite polynomials after a French mathematician, Hermite. And I won't list them here, but you can see the textbook for a list of the first 6 of these polynomials. Okay, so we've done, I realize, as often, a lot of algebra and power series and so forth. So let's look at a picture. These are the first 4 wave functions and the probability densities for the harmonic oscillator. So here on the left are the wave functions psi n. This is for n equals 0, n equal 1, n equal 2, n equal 3. So for n equals 0, the wave function is a Gaussian, and it peaks. And interestingly, it doesn't go to 0. It extends outside of the potential. Okay, so there's some chance for the quantum particle to be found outside where a classical particle could be found in the same harmonic oscillator. For n equal 1, it's interesting that it goes through 0 at x equals 0. And that's because it's an odd function, so it has to go through 0 there. For n equal 2, we get two humps. For n equal 3, we get 3 humps, and again, it goes through 0. Notice that these, for n equals 0 and n equal 2, these are even. For n equals 1 and n equal 3, they're odd. But now if we look at the probability density squared, an even function squared is an even function. An odd function squared is also an even function. So all these become even. That is, they become symmetrical around the x-axis, which makes sense because the potential is symmetric. We'd expect the same probability to the right and to the left. Okay, so but we still get for n equal 1 and n equal 3, the probability density at the x equals 0 is 0, because if you square 0, you get 0. Okay, and as we went up further, we would get a similar pattern, just more and more humps and more bumps as we went up to higher energies. Okay, so let's look at an example, a combination wave function. So consider a superposition, okay? So any solution to the Schrodinger equation, for example, psi 0 or psi 1, if we add them together, we get another solution because the Schrodinger equation is linear. So we can always add together a bunch of solutions and we'll get another solution. That's the principle of superposition, or the linearity of the Schrodinger equation. So here, since we're dealing with a harmonic oscillator, psi 0 is this function up here on the right, and psi 1 would be the first excited state, which is this function here. Okay, so the normalization constant, we would need to get that, and we can actually get the normalization constant, even though these expressions are kind of complicated. It looks like we might have to do some integrals of these things. We can actually get it just using orthonormality. That is, that each wave function by itself is normalized, and if we take the integral of one wave function times the second wave function, we get 0, since they're orthonormal or orthogonal. Okay, so here's how this would look. To find the normalization constant, we take integral from -infinity to infinity of our superposition psi star x of 0, psi x of 0 dx is equal to our a squared, and then we'd have to, since we have to square this, or take the complex conjugate times this back again, we'd get 4 terms: psi 0 star psi 0, psi 1 star psi 0, psi 0 star psi 1, and then psi 1 star psi 1. If we take the complex conjugate times this, we're going to get 2 times 2 or 4 terms. The first term is the normalization integral for psi 0, which is 1. The second term is the overlap integral between psi 1 and psi 0, which, since they're orthogonal, is 0. The third is the overlap integral between 0 and 1, which is, since they're orthogonal, we already said, is 0. And the last one, since psi 1 is normalized, is 1. So we just get a squared times 1 plus 0 plus 0 plus 1 is equal to 1. So notice we didn't even have to use the specific wave functions here. We didn't have to plug in these big expressions here. We just used the fact that they were either normalized or orthogonal to get the values 1 and 0. Okay, so solving for a squared would be equal to 1/2. So a would be the square root of 2 over 2. So then this would be our final wave function, or our wave function at the initial time t times 0 would be a times, which is the square root of 2 over 2 times psi 0 plus psi 1. And the interesting thing is, although it is built, this superposition was built by combining stationary states, right? Because psi 0 and psi 1 are stationary states of the harmonic oscillator. Their probability densities don't evolve in time. But it turns out the superposition has a probability density which does oscillate in time, and that's due to the different time dependencies of the two stationary states. Because these have different energies, when we put in the time dependence to make this time dependent, we get different exponential factors because the energy is involved in the exponent. And so when we take when we look at the probability density in time, we don't just get a constant, we get a time-dependent factor. Okay, so by combining stationary states in this way, we can get quantum dynamics, that is probability densities which actually oscillate or move in time. So that's kind of exciting. Okay, so just to very quickly sum up, this is concludes our unit on or our section on the harmonic oscillator. We've solved it using two methods, the ladder operators and the power series method. The ladder operators method is very nice and elegant and probably a little cleaner. The power series method is a power series applied to a variety of problems in math and physics, including the hydrogen atom. So that's why it was worth looking at that different form. And we see that they agree on both the energies of the harmonic oscillator and the stationary states, or the wave function psi n. And then we looked here just at the last at a combination wave function, seeing that when we combine two stationary states, we get something, we can find the normalization constant very readily, and we get something whose probability density oscillates in time due to these different time dependencies, due to the different energies of these two states. Okay, thanks for your attention, and I will see you in class.